Good morning, students. Welcome back to science class on the chapter magnetic effects of electric current. In the previous class, we have discussed how we can create magnetic field using the electric current. Okay, so first we have discussed current through a straight conductor. Then we had studied the current in a circular, magnetic field due to a current circular loop. Then solenoid. Okay, so we can decide the direction of the magnetic field, that is according to a right hand thumb rule. Okay, so here that thumb represents the direction of the current. The remaining four fingers we have to close like this. Then those remaining four fingers represents the direction of the magnetic field. Okay, today we will discuss what is electromagnet. Okay, you have studied, right, solenoid. See here, if you keep one magnet here, no, sorry, one soft iron core here, okay, or take one iron core like this. Okay, see, take a wire, just hold it like this. See, this is one iron core, okay, a piece of magnetic material like iron core. Okay, you have to use this, you have to hold that wire like this. Okay, see, then we call this as electromagnet. What is that? Electromagnet. See, electromagnet means a long tightly wound helical coil. A long tightly wound helical coil of metallic wire containing soft iron core in its core is called an electromagnet. Okay, or we can say it in simple words. See, a strong magnetic field produced. What is that? So we can produce a strong magnetic field inside a solenoid. Okay, a strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. Okay, the magnet so formed is called an electromagnet. So here we can see, now this is a soft iron core. Okay, here we have put that wire. Okay, so we can say that this is an electromagnet. So here we can produce strong magnet. So just imagine this is a piece of iron. Okay, this is a piece of iron. Take a wire and rotate like this, move like this. Okay, so what will happen? Then we can call it, then just pass a current. Then we can say that this is an electromagnet. Clear? What is electromagnet? Yes. So next move to force on a current carrying conductor in a magnetic field. Force on a current carrying conductor in a magnetic field. See, in the previous year we had studied, right, about force, gravitational force, and some kind of force. Okay, a balanced force, unbalanced force, frictional force. Okay, so now see here, you know already. See here, these are two bar magnets. Okay, so now I will bring this bar magnet the same sides. These two are like poles. Okay, same poles near to here. What will happen? Just I will keep here. What will happen? It moves away, right? It repels, which means it will move. For example, here. Okay, it will move like this. Correct? Okay, why? Because the unlike poles or like poles are repel each other. Why? Because we can say that here this bar magnet moved. Why? Because of some kind of force. You know, when the object changes, if you apply a force on object, then only positions of the object changes, otherwise it won't. Okay, so here the position of this magnet changed. Why? That is due to some force. Okay, so which kind of force here? So that force is called magnetic force. Why? Because here you bring the same pole or same side here, what will happen? They'll experience some kind of force. So that force is called magnetic force. Okay, and they move away from each other. Okay, sorry, this paramagnet will move away from this one. Means here like force repel each other. Repel is nothing but it is also force, right? Okay, so this force is called magnetic force. Okay, so now force on a current carrying conductor in a magnetic field. Force on a current carrying conductor in a magnetic field. Okay, see, just imagine this is a horse magnet. Horse magnet. Okay, just imagine. This is the battery. Okay, so now this is a one conductor. Okay, say soft iron core. It is connected. Okay, so this is the current direction. Okay, so now this is a horse magnet. Horse magnet. This is north side and this is south side. Okay, now see here. Uh, See here, now we have kept this conductor. Okay, this conductor between the magnets. Between magnets. So now this conductor it will experience on some kind of force. Okay, so that force is called magnetic force. Here, see here, when you turn on the key, means when you pass current, what will happen? So now this conductor it will move one side. Maybe it is move either this side or this side. We'll see later. Okay, so now here see, when you keep a conductor between a magnets, okay, when you keep a conductor and if you pass current to that conductor, if you keep that conductor between the magnets, so then it will experience a force. So that force is called magnetic force. Okay, we will study which side this conductor is moving, whether this side or that. We have one more rule. Okay, that is Fleming's left hand rule. Okay, what is that? Fleming's left hand rule. Okay, see, keep in your mind when you keep a conductor. Okay, you have to mount the wire like this. Okay, if you keep that conductor between the poles, between the magnets, then that conductor it will experience a force. So that force is called magnetic force. Okay. So now, so in which side that object it will move? For that we have one rule. Okay, so that rule is Fleming's left hand rule. See here, first three fingers of your left hand, first three fingers of your left hand, you have to hold mutually perpendicular to each other. You have to hold these three fingers, first three fingers, that is thumb, forefinger, and middle finger. You have to hold like this, mutually perpendicular. See here, now this thumb is perpendicular. See, if you hold like this, now this thumb is perpendicular to middle finger and forefinger. Okay, then if you hold like this, now this forefinger is perpendicular to middle finger and thumb. Then if you hold like this, now this middle finger is perpendicular to forefinger and thumb. Okay, so you have to hold the first three fingers mutually perpendicular to each other. Clear? Now, see here. Here, this thumb, see here, this forefinger. Okay, this forefinger which represents the direction of the magnetic field. What is that? Direction of the magnetic field. Then this middle finger which represents the direction of the current. Then this middle finger represents the direction of the, sorry, this middle finger shows the direction of the current. Then what about this thumb? Now this thumb which shows the direction of the force, or in which side that conductor will move. Okay, now see here, see, I will hold like this. Okay, I will hold like this. So now this is the magnetic field direction. Magnetic field direction is like this. Then this is the current direction. Okay, now we should know in which side that conductor will move. So now just release it like this. So now here the thumb, it is in, now this thumb is showing the direction this side, right? So then we can say that that conductor it will move in this direction. Clear? Suppose if you hold like this, see here, forefinger represents the direction of the magnetic field and middle finger direction of the current. Direction of the magnetic field is in this direction, then the current is in this direction, that is downward. Then in which side that conductor will move? Just release it. Then that conductor it will move in this direction. Clear? So here we use the Fleming's left hand rule to know in which side that conductor is moving. Okay? So clear it. So next move to electric motor. Okay, electric motor DC motors in a small toys. Okay. First I will draw the diagram. Okay, see here. So now we will study the working of electric motor or the working of DC motor. Okay, you know you have used it, right? That the DC motor. Okay, see here that DC motor. So here also same. So now here we should know. Now this is just a minute. Yes, see here. Here now first consider this coil ABCD. So we call this is a coil, or we can say that armature, and here two magnets, two powerful magnets, that is north and south. Okay, and this armature AB is connected to split rings. Okay, these two are split rings R1 and R2. For example, say this is a ring. Okay, it is a ring. So just like do like this. Then these two are split rings. Okay, next these two split rings are connected to brushes. Okay, those are carbon brushes, and two brushes we have connected battery. You know that the DC motor. Okay, so when you connect a battery, then what will happen inside that DC motor? So that DC motor, it starts to rotate. So here we can say that electrical energy is converted to mechanical energy. So we can say that why? Because so you will pass current. Okay, so you will pass current. Then what will happen? So that DC motor, it will start to rotate. So that's why DC motor, which converts electrical energy into mechanical energy. Okay, into mechanical energy. Armature ABCD is a current carrying coil. Okay. Next, field magnets. These two are north and south. These two are field magnets. So now the direction of the magnetic field energy, that is from north to south in this direction. Okay. Next, split rings. Split rings are commutator. Okay. We can call these two split rings are commutators. Okay. Now here now this AB is connected to R1 and D is connected to R2. So now these two split rings, these split rings rotate with this armature. Okay, these two split rings rotate with this armature. Okay. So now we will see the working. Okay. So now this is a coil. So now we should know in which direction that coil will move. Whether it will move upside or downwards. Okay. Now see here. First see the current. What is the current? So now current direction is now from positive to negative. So here connected here. So we can say that the direction of the current is first A to B. Okay. So direction of the current is A to B. Now current is moving in this direction. See here. Now here forefinger represents the direction of the magnetic field, and middle finger represents the direction of the current. So now current is moving in this direction. Okay, current is moving in this direction. Then magnetic field like this. Okay, now just release it. Now we can say that that coil is moving in that direction, or we can say here. Now, for example. Here these two are magnets. Okay, these two are magnets. This is north and this is south. Okay, now the direction is from like this, in this direction, the current direction of the current. Then I will keep, say this is a armature, I will keep here. Okay, or we can say that I will keep this book. Okay, so I will keep this book. Okay, just imagine here two magnets are there, south pole and this is north pole. Now the direction of the current is from direction of the magnetic field is north to south, that is in this direction. Okay. Now what about current? So now the direction of the current is from this end to this end. Current direction of the current. This end to now current is moving in this direction. Okay. So now we'll discuss about whether this book it will move in this direction or in this direction. Okay. Now see here, magnetic field direction and current direction. Now just release it. So now this thumb which shows the direction downwards, right? So then we can say that this book it will move downwards like this. Okay, like this. So now see here this AB cord, this AB set it will move downwards, and this ABCD it will come upwards. Okay. So then now this D it will come here, and C is here, and this is B and A. Okay. Yes. Now here also see here. Now this is AB and this is CD. Okay. Now we have studied what. So it will this book this side. Okay. This AB side it will move downwards. Okay. So now this AB it will go this side, and CD it will come this side like this. So now this is DC and this is AB. So once again same. Current is from now the current direction is from D to C. D to C, and magnetic field that is fixed. Okay, direction magnetic field that is fixed. That is from north to south. See, direction of the magnetic field, current, and just release it. So now once again that thumb is showing the downwards, right? So once again this DC it will move downwards. Then AB will come upwards. Okay. So once again back to the same. Now once again AB and DC, or we can say. So here now this is a north pole and this is a south pole. Okay, north pole, south pole. Now the direction of the magnetic field is from north to south, means in this direction. Okay. Now just observe here. Current is, say this is A point and this is B point. Now current is moving from A to B. Current is moving from A to B. Okay. Now see here. Now we will see in which direction this book will move. Now see here, magnetic field, okay, and say current direction. Now current is moving in this direction, right? Current is moving in this direction, magnetic field. Okay. Now just release it. What will happen? So now this conductor, see this book or this conductor, it is moving downwards. Clear? Okay. So this is the working of electric. Okay. Now here, what is the role of these carbon brushes? Because here these are very good conductors, right? So that's why we are using carbon brushes here. Then what is the use of these split rings? You know, it will rotate in only one direction. Okay, when you turn on the battery, if it rotates, say for example in this direction, then it continuously it will rotate in this direction only. When you change the polarity at that time also, at that time only it will change its direction. Otherwise it won't change its direction. It will rotate in one direction only. Okay. See, then what are the use of these split rings? What is the role of split rings? Okay. See here these split rings rotate with armature. Okay. Rotate with armature. Just a minute. Here, okay. So now these two split rings rotate with armature. Okay, if you won't use these split rings, what will happen? Then you have to rotate this even this battery also. Okay, you know, while using that DC motor, just you connect that battery. That battery it won't rotate with that coil. Okay, only this armature or this coil will rotate. Okay, so that's why we are using these split rings. Clear? Means here the current is always from positive negative. Once that current it will move through R1 to first AB, then while rotating, when DC will come this side, at that time also that current direction it will move from R1 to DC. Okay, so that's why we call this is a unidirectional. Here this armature it will rotate in one direction. Okay, so that's why we use split rings. So now listen here. Now, how to increase the speed of this armature? Okay, you know when you pass over your DC motors, some motors they will rotate with very huge speed, some will rotate with less speed. Okay, then how to increase that speed of rotation? Okay, so see here we can increase that speed of rotation one by increasing the current. When you increase the current, then also the speed of the rotation increases. Then you can increase the steer. When you use more number of turns, here just I use one turn, right? When you use more number of turns, you have seen right in that armature. When you open that DC motor, you can find there are so many windings, correct? Windings of copper wire. Okay, so when you increase the number of turns, if you increase the number of turns, then also we can increase the speed of the rotation. Okay. Next, when you increase the power of the magnetic fields, okay, if you have more magnetic, if you have magnets, then also we can increase the speed. Okay, so here this DC motor which converts electrical energy into mechanical energy. Okay, so this is the working of DC motor or electric motor. Okay, so here this is very important. Working and diagram is very important for 2 marks or 4 marks. Sometimes they will ask for 4 marks. Just to draw DC motor diagram and explain the working. Okay, so otherwise sometimes they will ask only draw the DC motor diagram. Okay, so this is very important for your examination point of view. So clear? Yes, sir. So in the tomorrow class we will discuss electromagnetic induction. Okay. So in electromagnetic induction we will study what the working of electric generator, how we can generate electricity. Okay. See here till now we have studied what we can generate magnetic field. We can generate magnetic field using electric current. Okay. Means when you just this is a wire, okay, when you pass electric current through this water around this current, what will happen? So magnetic field will generate. Okay, so here we are generating that magnetic field, that is due because